Yeah. Thank you, Mr. Chairman. Ladies and gentlemen, good morning. I'm sorry I cannot speak Chinese, but I guess that the translators will assist. I would like first to thank the organizers for inviting me to present you here what we are doing in Europe, how we are going to address CO2 emissions and fuel consumption from HDVs, heavy-duty vehicles. So the title of my presentation today is Developments of CO2 and Fuel Efficiency Measurements in Europe and Future Prospects. I will be talking about CO2 emissions from transport with numbers. So I will try to provide you a couple of graphs in order to show you what is the current situation in Europe in terms of CO2 emissions from transport. Then I will go through and explain what is the European Commission strategy. Then I will discuss and I will analyze the new simulation tool that will be used for certification purposes of CO2 emissions in Europe, and this is called Vector. Vector for trucks, but Vector also for buses and coaches, and I will provide some information with regards to the pre-pilot phase that we had a couple of months ago for these buses and coaches. Then the proof of concept activity will be described also. I will give you some information with regards to the timeline, the timeline in Europe and the regulation that we are developing there. And of course, at the end, there is a Q&A session where I will be more than happy to address any question that you might have. As I said at the beginning, let me just provide you a quick overview of greenhouse gas emissions by sector in the European Union of the 28 member states. So you see there that for transport, we have more or less 20% of the total CO2 emissions. So 20% of CO2 emissions in total comes from transport. If we move now to CO2 emissions from transport in the EU 28, then you see that from road transportation, I'm talking about HDVs, heavy-duty vehicles, buses and coaches, as I said before. So from road transportation, you see that we get more or less the vast majority of all transport emissions, and this is 72% of total CO2 emissions. And then if we try to split that down to road transport emissions, which is, let's say, by type of road vehicle, then we see that for cars and light-duty vehicles, as we call them in Europe, vans, so from cars and vans, we get 70% of CO2 emissions, and then from heavy-duty vehicles, buses and coaches altogether, then we get 30% of CO2 emissions. So it's 70 and 30% of CO2 emissions by type of road vehicle. The European Commission issued a couple of months ago, actually last July, the strategy for low emissions mobility. And if you are interested in downloading this document, then you get all the information here, so you can search for this document on the internet and you can easily download it. In this document now, it was clear that, as you see in the last paragraph here, that the Commission will make full use of all available data, including the simulation tool developed in close collaboration with stakeholders in order to address the CO2 emissions and the fuel consumption issue in Europe. Let me, before I move on, let me just give you very briefly an idea how the certification legislation works in Europe, because you might be familiar, but you might not. So in the European Union, certification of motor vehicles takes place under the type approval legislation as defined in the 2007/46 Framework Directive. We call it Framework Directive, and this is the type approval legislation. This Framework Directive is currently being transformed into a new regulation. DG GROW, this is another part of the European Commission. DG, means Directorate General. So DG GROW has prepared now a new legislative act on HDV certification under the Regulation 595/2009. And this Regulation 595 is the famous, I would say, regulation, the Euro 6, as we call it, regulation in Europe, which mainly deals with HDV's emission pollutants, but not with CO2. So the text has been adopted by the Technical Committee of Motor Vehicles only last week on the 11th of May. So what I'm presenting here now, I will say that is quite new. It's only one week old, let me put it like that. And the text, as I said before, has been already adopted by the Technical Committee of Motor Vehicles last week. Now, with regards to Vector, which is the simulation tool that will be used for this certification of CO2 emissions, we had some tests. So we performed some tests on trucks from 2012 to 2014. And we performed, these tests in order to demonstrate, let's say, Vector's accuracy and reliability. We are not able to introduce any simulation tool in the regulation if the tool as such is not accurate and is not reliable. The software, the tool, was further tested and improved in 2015 during the pilot phase, as we call it. So we had a period which was the pilot phase, and we further tested the software and the simulation tool. Now the tool is ready and will be the backbone of the certification that I described a couple of minutes ago that will be introduced in the new regulation. So this is now the tool, the Vector tool. First of all, Vector stands for Vehicle Energy Consumption Calculation Tool. It's a simulation tool that can be used in order to calculate both the fuel consumption and the CO2 emissions from the whole vehicle. And I would like to mention here that I put, with bold, and I underlined the whole vehicle. And I will come back to that in a minute. So Vector has been developed by the Commission, the European Commission, and we had some support from the Technical University of Graz, which is in Austria. I would say that we started more than 6 years ago, so it's been more than 6 years since we started developing the simulation tool. ASEA, which is the European Association of Manufacturers, OEMs and component manufacturers have been also involved in the whole process, and they provided key input but also test vehicles. It's important that we get also, some test vehicles in order to check the tool and to perform, several other verification tests. So, if we are talking about passenger cars, I would say that it's quite simple to measure CO2 emissions. So you just get, a passenger car, you put it on a chassis dynamometer, you start running the chassis dynamometer, and then you measure the CO2 and the fuel consumption. So this is, I would say, pretty simple. But if you are talking about an HDV, if you are talking about a heavy-duty vehicle, only on this picture here, there are more than 100 different types of vehicles. So think about any chassis dynamometer that we should get in order to test, all these vehicles. It's almost impossible. We cannot really use any chassis dynamometer in order to test all these different types of vehicles. So for HDVs, for heavy-duty vehicles, we know that these are more complicated than light-duty vehicles. And this is mainly because, for example, you can have a low, a medium, a high, a long, a short cab, or any other type of cab. You can also have 2, 3, 4, 5, or even 6 axles with different configurations like 4x2, 4x4, 6x2, etc. You can also have different tires for each axle, which means that you can have single tires or twin tires for each of these axles. This is something very important. The same engine can be used, on, let's say, different vehicles, and the same engine can be fitted also with different gearboxes or with different axles. So that means, another configuration again. Then, the truck can be a rigid, can be a semi-trailer, can be a tractor, or if you are talking about buses, then this can be a coach, can be a bus, or can be even a city bus. When I'm saying coach, I mean these buses that normally, in order to make it clear, we call, in Europe we call coaches all these buses that they perform, let's say, long journeys. For example, starting from here, going down to Shanghai. So this is a coach. And of course, you can have any of the combinations mentioned above. That means that at the end of the day, we might get millions of different combinations. So if you are talking about millions of different combinations, then you see and you realize that it's almost impossible that we use any chassis dynamometer to test these HTVs. This is the graphical user interface of Vector. So this is just a snapshot of Vector graphical user interface. And these are some, let's say, more snapshots of Vector. So you see, for example, here now that we have, a job file which is for the vehicle, and then we need to introduce details about the vehicle, number of axles, gross vehicle weight, and other parameters. We have something similar for the gearbox. So we need to introduce, the number of gears. We need to introduce, a couple of other information for the gearbox. And then we have also for the engine. So we need all this kind of data in order to run Vector. So Vector now has got two modes, and this is very important. One mode is the declaration mode, where all generic data and the test cycle are allocated automatically as soon as the vehicle class is defined. And I will come back later to this vehicle class. And there is also the engineering mode, where the user can select and change all input data to allow recalculation of test data. Which means that if you are running, let's say, a certain test, and you want to change something, then you need to use the engineering mode. But if you are running an official test and you want to get, the certification, for example, or the certificate, then the declaration mode needs to be selected. In the declaration mode, you are not allowed to change a lot of things. But in the engineering mode, you can change a lot of things. And then, what is the Vector output? So the Vector output now, you see that in the declaration mode, the fuel consumption and CO2 emissions are automatically calculated for all test cycles allocated to the vehicle, for the average payload and full load. And the results are given in grams per kilometer, grams per cubic meter kilometer, grams per ton kilometer, or if you are talking about buses and coaches, grams per passenger kilometer. We are also considering other metrics that can be used at a later stage. A few details now with regards to the model structure. So we are talking about 4 main modules. So you see M1, M2, M3, M4. And these 4 different modules, I can tell you that they are very, very, very complicated. And there is a very complex structure in these 4 main modules. So you see, for example, that for each of these modules there are some sub-modules, and then for each of these sub-modules can have, sub-modules, etc. So you see here or even here. So it's really complicated, the structure of the tool. In order to show you the complexity of the tool, have a look on this formula here now. So the simulation of the engine power comes from this equation here, from this formula. So this is only for the engine power. Only for the engine power. Of course, I'm not going to go through the whole formulas. I'm not going to go through all these equations that are used in vector, but this is only to show you, as I said before, the complexity of the structure of the tool. I mentioned before 5 different mission profiles. So I would like to make clear now that I'm talking about 5 different mission profiles for trucks and 5 different mission profiles for buses and coaches. If you want to use another word instead of mission profile, then I would say driving cycle, but it's not exactly the same. That's why we use the mission profile here. So for trucks, we have the urban delivery, regional delivery, long-haul, construction, and municipal utility. And then for buses and coaches, you see that we have the city bus heavy urban, the city bus urban, the city bus suburban, interurban bus, and coach. So these are 5 different mission profiles for buses and coaches. This is just an example. So this is an example of the long-haul cycle for trucks. So you see, for example, that the total distance for the long-haul cycle is 110 kilometers, more or less. And then you see also that the maximum speed that the vehicle can achieve during this mission profile is 90 kilometers. So this is the limit, in Europe, on European roads, maximum speed of 90 kilometers. And then, of course, we have also the acceleration and deceleration during this mission profile. This is how the long-haul driving cycle looks like. This is how the regional delivery cycles, because we have 2 different regional delivery cycles, both look like. And this is how the urban delivery looks like. And then you see, for example, what is the maximum speed, what is the distance travel, etc. All these details are clearly identified in these mission profiles. I mentioned before some vehicle classes, if you remember, and I said that I will come back to that. So we have already identified 17 different vehicle classes for trucks. And then you see here these 17 vehicle classes, 1, 2, 3, 4, down to 17. And then here you see the different configuration. So you have, for example, 4x2, 4x4, 6x4, 6x2, etc. And then you have the chassis configuration, which is either a rigid or a tractor. And then this is the gross vehicle weight of the vehicle. So we have developed, this table with all vehicles that are sold at the moment in the European market, and we created these 17 different vehicle classes. And then these are now the mission profiles that I mentioned before for trucks. So you have the long haul, you have the regional delivery, so you have the long haul, you have the regional delivery, etc., the urban delivery, all these mission profiles. And then we have also the long-haul EMS. This EMS stands for European Modular System, and these are the extra long vehicles that we have now in Europe, especially in some European countries. And we wanted also to include, this long-haul or the extra long vehicles in our new regulation. What about the fuels now? What are the reference fuels for testing? So for Vector, we are considering these 5 reference fuels, as we call them, and these are the 5 reference fuels that are already included in the Euro 6 regulation. So you see that we can calculate CO2 and fuel consumption from diesel, ethanol, LPG, natural gas. All these fuels are included now in the simulation specification for this test track. And then, of course, we need to apply certain formulas. We need to perform some calculations in order to end up with the aerodynamic drag. These are now the 5 different classes for buses. So you see here, number of axles. So you can have a bus with 2 axles or with 3 axles. Then the bus can be 4x2 or 6x2. Again, the chassis configuration, and then the mission profiles that I mentioned before, heavy urban, etc. Buses are not that easy to be simulated like trucks. Why? Simply because for buses we have a high share of energy consumption, which means that if you compare a Euro 5 semi-trailer 28 tons with a Euro 5 city bus, then you see that for the truck here, the auxiliaries losses, as we call them auxiliaries, is more or less 5%. And when I'm saying auxiliaries, I mean mainly the engine cooling fan, the alternator, the air compressor, the steering pump, and of course the air conditioning compressor. If you move now to the Euro 5 city bus, which means a bus which runs, in Beijing city center, for example, then the auxiliaries losses here can be 26%. So from 5% for a truck, this can be 26%. Why? Simply because you get, more losses for certain auxiliaries that are used on buses and coaches. And this is also now another example in order to show you the complexity of buses. And this is a coach that we compare with the city bus. So for a coach, the total losses of the auxiliaries are more or less 12%. And for a city bus, this can be 22%. So it's almost double the amount of losses that you get for a city bus compared to a coach. That's why we always say in Europe that a coach can be simulated easily like a long-haul truck. So if you want to simulate a coach, this is more or less, or can be simulated more or less like a heavy-duty long-haul. This is the vector core, and the tool that has been used also in order to take into account the bus auxiliaries losses. And then I move to the proof of concept activity, and this is an activity that we performed in Europe, especially in Italy. My colleagues at the JRC, which is the Joint Research Center of the European Commission in Italy, they performed, tests with two trucks, one Daimler and one DAF. So we had, a DAF and a Daimler. We used the proving ground test of Iveco. Then we had also the JRC dyno testing, and then we had also some PEMS equipment in order to check, the on-road emissions. This is very quickly, this is the equipment used for these tests. And then you see here, for example, the torque meters that have been used in order to calculate, certain and get certain information from the vehicle. And these are the test vehicles now. These are the test vehicles that we used. As I said, it's a Daimler, a semi-trailer, a tractor with a trailer, and this is a DAF, a rigid one, 2 axles. So this is a Euro 6 vehicle, the Daimler, and the DAF one was a Euro 5. This is the test route. So this is the test ground at Iveco in Italy that we used in order to make all the aerodynamic tests. And this is the route that we followed under real-world conditions. So this is what the distance traveled, in order to calculate all these fuel consumption and CO2 emissions. We performed a similar activity for buses and coaches, and we call it pre-pilot phase. And I participated in this pre-pilot phase almost a month ago. So you see now that we had a bus there, a suburban bus. And these are, the wheel rims that we used also on this bus. And this is, the PEMS equipment. The whole vehicle was fitted, with this PEMS equipment. And we used also JRC's test facilities in order to check the vehicle. And we put also the vehicle on a chassis dynamometer and we measured the vehicle. What are now the report's conclusion and the follow-up? We concluded from the proof of concept activity, and this is the most important for us, that the simulated fuel consumption was calculated with a range of plus minus 3% from the real world measurement, or even less, which means that the accuracy of our simulation tool is more or less plus minus 3%, and I think this is very, very important and is something that we are very proud of. The full report of this study, if you are interested and you would like to get some more information, can be found on our website. So you can easily download the full report that we published, this study. And then I'm just at the end of my presentation, and I would like to give you some information with regards to the timeline. I'm talking about the timeline for trucks only, because for buses we are supposed to be 1.5 or even 2 years, let's say, late. With regards to trucks, vector development is still ongoing, and I think this will be ongoing in the future as well. Dissemination and trials, as I said, we started back in 2013, and we performed, all these trials until mid-2016. Preparation of possible legislative proposals, as I said, it has been voted only last week. We started in 2015, and the text and the Technical Committee of Vehicles has adopted now this legislative proposal. And then the possible first year of reporting will be 2019, which means that we'll get all the data from every single vehicle in 2019, and we will be able to create a kind of database of CO2 emissions. So this is the end of my presentation. I think I'm not late, Mr. Chairman. I tried to keep it, in 30 minutes. I would be happy now to address any questions, but please, if there is any question after this presentation and you think that you need more information, do not hesitate to send me an email. My email address is given at the end of this presentation, so please feel free to contact me if you need further information on Vector. Thank you very much.